Hey guys, Mr. Kyle, Myers Mathematics, and let's jump into our video for today. Why the P-series is the best test, and let's say the best test for convergence, testing convergence and divergence. And I'll also probably start with the one that I think is the least useful out of all of these. And if I missed one, let me know. There's a lot, and I really don't care too much about this particular section because I think having to do all these different tests is really dumb, because one of these tests is way better than the others, and if you kind of tweak it a little bit, is actually sort of like Sauron's ring. It's the one test to rule them all. So let's go ahead and look at some of these, and I won't necessarily go in order here, but let's talk a little bit about what they are in case you weren't totally familiar with this, if you're on this unit, and then also what is wrong with them, and kind of, I think I'll probably just save the best for last here, so you kind of narrow it down. Okay, so go ahead and pause the video and look at these and see if you know which one is the best. I think it's P-series, but why don't you go ahead and find out? Think about which one you think is the best and why. And if you disagree with me, you're welcome to put it in the comments and let me know, and we'll have a nice discussion. But let's go ahead and jump in. So the one that is the least useful out of all of these has to be the limit test. It's really dumb. Basically, what it says is that if the limit is not equal to 0, the limit as n goes to infinity. If it's not 0, then it's divergent. So if that, then it's divergent. Then divergent. Okay? And the reason why this is really dumb is because the whole point of a convergence test is so that you can tell whether it's converging or diverging. This is not actually going to tell you whether it's converging. If the limit is 0, that just means that I don't know for sure that it's diverging. It still could diverge. So the limit test is probably the least useful out of all of these. Okay, and the limit comparison test is, not much better. So we'll do that one next here. Limit comparison test. Okay, so essentially what you do is you get like a cleaned up version of the first thing, and then you compare by using a limit. So you're like, oh, hey, well, if the limit is this, the limit of A and the limit of B, and you kind of make A or B like a cleaned up version of the whole thing. So in order to do that, you're kind of doing like P-series anyways, and you test both of those out. And then basically if A and B are both if they're both convergent, then it converges, and if they're both divergent, then it diverges. I'm not as familiar with this one, as you can tell, because I think it's also really dumb. And it's one of those ones where it's like, it's a lot of work for not a lot of like clarity on whether it's really actually converging or not. So also not one of my favorites. Let's see, which one else? I actually really don't mind the ratio and root test, so we'll do those a little bit later. Alternating series. This one is also kind of dumb, because it's basically like, hey, if you have one of these things, and then you have some other stuff going on, AN, just some other stuff going on, then here's what happens. If the limit of AN is 0, then it converges because of that little -1 to the n power thing. And if not, then it doesn't. So alternating series is actually kind of useful, but irrelevant whenever we look at how awesome P-series is. Comparison test, it's okay. It's okay. Actually, I kind of wanted to label this one yellow. I'm kind of going on a spectrum here. We'll say this one's yellow. So we'll go ahead and do this here. This is going to make it look a little murky, but it's whatever. All right, so comparison test is okay. You're kind of just like, it's similar to limit comparison, except you're not taking the limit. You're comparing two things that are really similar. So basically, let's see, if it's like, it's basically you clean it up. You do a cleaned up version. And if that cleaned up version, so AN is the original, B sub n would be like the cleaned up version. So if B sub n is like greater, and if B sub n is greater and it converges, so if B converges, then A converges. And then if it's the other way around, if your cleaned up version is less than A, then if B diverges, then it diverges. Basically, you know, if your cleaned up version is always bigger than your other version, and it converges, then it converges. And then if it doesn't, then it diverges. Okay, so comparison test, it's kind of useful. You kind of have to get the hang of it, do a couple examples to kind of get used to the comparison test, but it's not too bad of a test. Kind of makes sense, and it works. It does tell you whether it converges or diverges, so it's kind of useful. What else? Alright, I've gotten past all the ones that are like just kind of okay. So I actually kind of like, I'll use green now, I'll use blue for like some of the best ones. But I kind of like these guys. These guys are okay. Ratio test. A ratio isn't necessarily a fraction, but it's kind of what it means. It means to do a fraction. So you basically, everywhere you see an n in your problem, or if you're using k or whatever letter you're using for your sum, everywhere you see an n, add 1 to it. So an plus 1, and then divide that by the original. And then basically, it sort of creates this scenario where the limit test actually kind of matters. So instead of the limit not equaling 0, meaning divergent, now we kind of have a series of things where the limit could be, could actually tell us whether it really converges or not. And the same thing with the root test, actually. So before I tell you what those limits are, root test, well, root test is kind of what it sounds like as well. You kind of just take the root. So you take the nth root of your thing. An is always the thing. It's the thing that you're doing the infinite sum of. And then if you do either one of these tests, the ratio or the root test, then you have this really kind of a cool scenario. So they're kind of useful tests where the limit as n approaches infinity, it's either going to be 0, and actually from 0 to 1, or it could be 1, or it could be more than 1. All right, and I'm going to put this in interval notation here. So if your limit is between 0 and 1, and I think it could include 0, actually, so that's fine. But if it is between 0 and 1, then we know it definitely converges. If it's exactly 1, it's sort of like back over here with the limit test, when the limit was 0. If the limit is 0, then it's inconclusive. We don't know if it converges or diverges. Well, now, if we do either the ratio or root test, 1 is that new magic number where you just don't know still. It's inconclusive. Oh my gosh, I cannot spell. Inconclusive. Whew. It's tough spelling when you do math for a living. I blame spell check. Okay, so converges, inconclusive, and then if it is greater than 1, any number greater than 1, then it diverges. So actually kind of useful. I kind of like those. They're okay. And the tests are fairly easy to do because they actually kind of make sense. They're not really weird and vague like the limit comparison and the comparison tests. Those are probably some of my least favorite to actually do. The limit test is really easy to do. You just take the limit. But it's only going to tell you if it actually diverges or it doesn't. You know, so if we look at the limit test, not the limit test, sorry, the ratio or root test, then the limit actually kind of does something for us. Okay, so I've hit all of those. I saved geometric series because geometric is actually kind of nice too. It basically just says that if we have something in the form a are, I like to use K. I know we've been using in the whole time, but it spells arc. So I don't know, it's because arn is not a word, but arc is. So I'm going to use K for this just because. So if we have ARK, if it's the sum as K equals 0 to infinity, if R is a number between 0 and 1, then it converges. If it's not, then it diverges. That's pretty much it. And I believe we would say it's the absolute value of R. Okay, so it could be like a negative fraction, positive or negative fraction, pure fraction. Then it converges. If not, then it diverges. So that's pretty straightforward as well. It's easy to check, easy to see if it's in that form already. Pretty easy to do. I also saved integral test because integral test is actually the best test if you want to find the value. If you want to find out what the actual value is, if it's not the geometric series, then integral test is really good because the geometric series, there's a pretty good test for that. We can actually figure out what it's equal to with the geometric series or the integral test. Because basically the integral test says, hey, if I take the integral from 1 to infinity, then it equals the answer. So if I get an answer, then it obviously converges on that answer. And if I don't get an answer, if it's infinity and beyond, then it diverges because infinity is not a number. So pretty useful. And also because this is Calc 2, you've probably gotten at least decent at integrals. So if it's an integral that you can take the integral of, and it's not too much trouble, shoot, why not? Take the integral of that sucker. And gives you the answer. Okay, so I think I've done all of these. Let's check them. So 1, 2, did that, skip p-series, blah, blah, blah. Okay, so here's why p-series is the best. You ready? Getting to the actual question of the day here. P-series test. The reason why this is amazing, and the reason why it's better than all the others, is because the rule says, oh, well, it's just this, and p has to be greater than 1. Okay, but it's not just this, because if I have the sum of, let's say, 3x squared plus 1 over 4x cubed. Okay, here's what you do. You just focus on the big dogs. This is kind of what the comparison tests do. Okay, so the comparison tests are useful because they tell you, hey, just focus on the big stuff. Just look at the biggest stuff, and then we're going to compare them either using a limit or just straight up putting them side by side and seeing what happens, okay? So that's kind of what we're doing here, okay? I'm kind of like taking a little bit of each of these other tests, the good parts out of these other tests, and putting them into p-series, okay? P-series is like Sauron's ring, okay? So just hear me out. All the other rings were given to those people and dwarves and elves because they were like, oh, it'll give you power. But then the ring, Sauron's ring, was always meant to control the others. So this one, this p-series test, it takes all the good things out of all the other tests, and you can put it into p-series and make it the one test to rule them all. So let's look at this. If I just use kind of a comparison here and just look at the big dogs, okay? You just want to look at the big dogs. Everybody else does not matter. Whoever the big dogs are. The big dogs are this guy and this guy. Okay, so if I just squeeze out the big dogs here, that would be 1 over x. That diverges because it's 1 over x. P has to be greater than 1. There you go. It diverges. Now, what if I throw in one of these guys? Okay. Well, if p is exactly 1, if p equals 1, then it would diverge as long as I have one of these guys. Okay. When p is exactly 1, it diverges, but it does what I like to call conditionally diverges. Okay, it's not like a term that's normally used. They talk about conditionally convergent, but I like to talk about this thing called conditionally divergent because it's like two sides of the same coin. If you have this little negative 1 to the n power, it kind of pushes it over the edge. Okay, so if it's conditionally divergent, if it just barely diverges when p is 1, if I multiply it by that negative 1 to the n power thing, now all of a sudden it diverges. So this thing here, if it would be, let's say all of this is an, well, if all of that is an, and then I take an and multiply it by negative 1 to the n, then it now converges. It converges now because of that whole alternating series test. The alternating series test basically says, hey, if the limit is 0 of the other thing, then that means it's conditionally divergent at least. It's at least conditionally divergent. And then the negative 1 to the n pushes it over the edge, and now it converges. Conditionally converges. Okay, so that handles all of that. Now, what about if it's something else? Well, if it's not a polynomial, let's say. Well, if it's got roots in it. So if it was x over the let's say x to the 5 halves power minus 1. Okay, well then you just look at the big dogs. You see what the difference is, and I would clean this up. So x over x 5 halves, which would turn into 1 over x to the 3 halves, which is bigger than 1, so it converges. Right? So it doesn't matter if you've got a fraction power, you can still compare them one for one. What about a limit? Not a limit, sorry. A logarithm, the other L word. If you have a logarithm, right? What about a log? Well, a log is going to be, basically it's going to be like between 0 and 1. And you're like, what? Between 0 and 1? What? So logs are between 0 and 1. What do I mean? I mean, every number, you can kind of write it as like a power, if it's a polynomial, right? So like x squared, right? So if I have a log of n, then it could have a power that's kind of between 0 and 1. So if I put log x over, let's say, x squared, then this could be as much as 1, but not equal to 1. It could be up to or including 1. And this one is a 2. So at most it would be almost 1, which means the bottom is still more than 1 bigger than the top. Just barely, so this would actually converge. Logs, you can kind of ascribe a number for a power that's between 0 and 1. Not including 1, though. So 2 has to be more than the top, more than 1 bigger than the top, because the top cannot be equal to 1. If it was equal to 1, it would be exactly 1 away. It's not, so that would converge. What about exponents? Well, exponents are not even powers. They're way beyond powers, so you just compare them 1 to 1. I mean, if it was like 2 to the x over 3 to the x, 3 is bigger. 3 is the bigger dog, and since the bigger dog's on the bottom, that's going to converge. And that's it. All right, that's where that whole ratio and root test stuff comes into play, is with figuring that out. But basically, if you have exponents, exponentials, the bigger exponential wins. It doesn't matter by how much. It doesn't have to be by a certain amount. Like literally, it could be like 2x over 2.1x, and that would converge. All right, p-series kind of doesn't really apply that much anymore because we're on a whole different level. But basically, you're still kind of doing the same thing. It's like the bottom has to be bigger than the top. When you can say that, oh, I can ascribe a number to this, p is a power. If the power is a certain number bigger than well, if x is the power, then we look at the base number, and basically if the base number is even a tiny bit bigger on the bottom, then it'll converge, even if it has a bunch of other stuff going on. So let's look at a more complicated example. What about 2 to the x, just because I seem to like that number, plus x squared plus, I don't know, 5x to the 12th power, all right? So that's ridiculously big, but if I put this over 2.1 to the x, is that going to converge or diverge? None of this other stuff matters, because exponentials are so much faster than polynomials, like ridiculously faster in the long run as you go to infinity. So none of that stuff matters. This would converge. Doesn't matter how big that power is. Doesn't even hold a candle to an exponential function. So you wouldn't even have to worry about it. Okay? So that is why p-series is the best test for convergence and divergence. You can take a little bit of what's useful about these other tests and kind of put it into p-series and kind of make it the best test, the absolute best one. Okay? And if you are like, well, I have this problem and p-series, not even your version of p-series, handles it, I challenge you to let me know what your problem is, and I will show you in the comment, like I'll comment your comment, and I will show you how p-series can solve every single problem. Any sum from 1 to infinity or 0 to infinity or whatever can be solved using my version of p-series, which is the best out of all of them. All right, so I challenge you to try to prove me wrong on that. But anyways, if you haven't already grabbed my awesome free guide, it is the 5 math mistakes everyone makes and how to avoid them. It is on my website, myersmathematics.com, and I'll put that link in the description below. Also, I made a limit video. It's an infinite limit video, and it kind of talks a little bit about the hierarchy of which things go faster to infinity. So I'll put a link for that in the description below as well, and you can check out that video. It's super, super helpful, and that is what I'm here to do, try to help you to tackle all your math classes. So if you want to see more videos like this for any class between Algebra 1 and Calculus 3, let me know in the comments below. Like, subscribe, and I'll see you in another video.